let's talk about the graphs of the sine and cosine functions. This is a very important topic, and it is for sure one of the most important topics in all of trigonometry. Okay, and one of the things that makes it so important is not just that the general graphs of sine and cosine are important in themselves, but these graphs also have a way of connecting the intimate tie of trigonometry and the trig functions to circles. And so I've come up with a great tip that will help you to never forget about this tie between the graphs of sine and cosine and the circle. So stay tuned for that tip. Okay, now the title of this video is Overview of Sinusoidal Functions. So you might be wondering, well, it seems like we're about to talk about the graphs of both sine and cosine. Well, the term sinusoidal applies to both the graph of sine and cosine. Now, I'll explain more about that later in the video. Okay, so let's say we've just invented trigonometry. We invented the subject. We defined the trig functions. You know, we've done a lot of work with all of the subject matter that we've learned up to this point in the course, but we've yet to think about the graphs of these functions. Well, how would we graph the trig functions? Well, and specifically here, we're talking about we're starting with the sine and cosine functions. Well, same way you graph any function, how we learn to graph functions in algebra. We would get whatever coordinate system we want, but we're going to do this on a Cartesian coordinate system. The function value, the trig function, is on the y-axis. The input will be x, and yeah, the independent variable is theta or x is the angle. That's how a trig function works. You input an angle, and then you do the trig function, right? The definition of trig functions. The general definition doesn't require a circle. You've got your angle measured from standard position. Here's the terminal side, or the initial side. You pick any angle, and that defines where the terminal side is. So there's the input. The input is an angle, but it's kind of confusing because we put x here. So like this would be theta, you can think about. So this is happening in its own world, independent from this coordinate system. So this is x and y. So these two x's aren't the same x. Okay, so based on an input angle, you pick a point along the terminal side, any point you want, along the terminal side line, and then you make the right triangle with perpendicular along the horizontal. And then this point has coordinates, x and y. In this case, it'll be a negative x and a negative y. And then all the trig functions are defined from there. And there's a radius here. Sine is y divided by r. Cosine is x divided by r. You do SOHCAHTOA with the reference angle to get any of the trig functions. So that's it. That's the input is some angle along the independent variable axis, and the output is, okay, you go to the trig function. If we're doing f of x is sine x, then it's just going to be opposite over hypotenuse for whatever the input, right? So if we wanted to do a graph of, let's say, sine of x, with all the knowledge we have up to this point, well, what we could do is we could make a table with some input angles, and then the corresponding sine of x, that's f of x, right? Let's say this is sine x. And we could pick a bunch of special angles, as well as any angle that has a reference angle that's a special angle. So we could, and then also quadrantal angles. So 0, 30, 45, 60, 90, 120, 135, 150, 180, etc. And then to get sine of x, we just use the reference triangles. Okay, now we could do this in degrees with the independent variable axis being degrees. But again, since when it comes to math formulas and calculus and anything outside of just visual geometry, we'd rather work in radians. So let's go ahead and do this in radians, which is not a problem. So we'd make a table with the corresponding sine value of pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, etc. Using the reference triangles just like before, same thing. So then we'd come and plot those values corresponding to the special angles or any angle that has a reference angle as a special angle. We plot those values, and then we would connect all of those dots with a smooth line, as smooth as we could draw it. Okay? Now, if you think about it, though, what's going to happen is that clearly, once we, with sine and cosine, the domain is all real numbers. You can input any number from negative infinity to infinity, and you're going to get a value, right? So once we got past, so we're in radians, we go from here's 0, we go to, let's say here's 2 pi. Okay, so we're plotting the points all around from 0 to 2 pi. That's where we'd start, right? We're starting with the special angles that are between 0 and 2 pi. But once we get to 2 pi and go past 2 pi, we're going to be doing we're going to get the exact same pattern that we got between 0 and 2 pi. There's no way that wouldn't happen. That's 100% going to happen. It's not possible for us to, so we get to 2 pi, now we're going past 2 pi. There's no way that we're going to all of a sudden start doing something different than what we did before, based on the definition of trig functions, because the trig functions, the definition is that any coterminal angles are going to have the exact same trig function values, right? If you got, here's pi over 6, and so 2 pi plus pi over 6 would be what? 2 pi, so 6 over 6 times 2 pi is 12 pi. So 12 pi over 6 plus pi over 6 is 13 pi over 6. So this corresponds to 13 pi over 6. You do the exact same procedure. This is 13 pi over 6. And so this is actually the unit circle, but even you can think about this from the general definition. You just get the coordinates of this. This is the unit circle. What are the coordinates of this point? Like the y coordinate of this point on the unit circle, that's the sine value, right? Well, if theta is 13 pi over 6, this is the triangle in the unit circle. The radius is 1. To get the coordinate, that's the sine value, right? So it's 100% you're going to get a repeating pattern over and over and over again every time you go all the way around the circle, meaning you go one full rotation. Once you go a full rotation, you're going to be repeating the same pattern. And we could go in the negative direction. If we think about, so if we went, instead of, starting at 0 and going in this direction, if we went the other direction, well, it wouldn't be, we wouldn't start with the same pattern right at the beginning, because now we're starting in the fourth quadrant, right? But the idea would be that if we went to, this is negative 2 pi, the pattern would start here. So we got some pattern starting at 0 and then going to 2 pi. It's going to be the exact same pattern going from negative 2 pi all the way to 0. We would just be, if we started at 0 and went to negative 2 pi, we'd be going through that pattern in reverse. Okay, so what we could do is we made the plot between 0 and 2 pi. We plot it, connected the dots with a smooth curve, and we could actually say, okay, I'm just going to when I go from 2 pi to 4 pi, I'm just going to just draw the exact same pattern, right? And when I go from negative 2 pi to 0 or negative 4 pi to negative 2 pi, I'm not going to make another table. I'm just going to draw that, just match the pattern, do the exact same pattern. What do we get? What does it look like? It looks like this, okay? Well, I mean, this is computer generated. I guess it would be like a rough sketch, but this is sine x. Okay, so 2 pi is like 6.2 something. You see, this is like 6.2 something. And starting at 0, if we go all the way to 2 pi, we see that what happens after 2 pi, you start again, right? You're going to start again. You would just do this exact same pattern all the way to 4 pi, right? You see how it restarts, and now when you go in the negative direction, if we come back to negative 2 pi, there's the pattern. Okay, now before we continue, I want you to note something. Note that in this video and in this entire section, we're strictly focusing on the graphs of sine x and cosine x that haven't been shifted left or right or up or down. Okay, we're going to talk about later in the video the idea of maybe we could multiply this by 2 or something, or like scale it up, like do a stretch or shrink about the y-axis, or a stretch or shrink about the x-axis. We're going to talk about that. We are thinking about stretching or shrinking about the x or y-axis in this section. And also we can think about flipping the sine or cosine about the x or y-axis. But right now there's no thought about the idea of shifting sine x or cosine x up or down or left or right. Okay, so it's important to keep that in mind, because when you're thinking about what are the fundamental properties of the sine function and of the cosine function, you have to be thinking about the basic function, just sine of x, cosine of x, completely untransformed, unshifted, or unstretched or shrunk about any axis, just like this, right? You start there, but then you really don't want to move it translated about the x or y. And one of the reasons why you can think about the case of why this is because, okay, if we did the same graphing process but with cosine of x, what do we get? So here's cosine x. Okay, well, it looks just like sine x. All right, now if we put them on the same graph, so the red is sine x, the blue is cosine x. Well, it looks like cosine x is just a horizontally shifted version of sine x. And in fact, that's exactly what it is. And so you see, that's one reason why to study the graphs of sine and cosine x, there's no shifting, right? If you shift at all horizontally, specifically horizontally, but even vertically, then you don't have sine or x or cosine x anymore, right? But I mean, that's a good way to study the basic fundamental properties of any function. You don't start without shifting them, right? But specifically in this case, it's a big deal. There's no shifting. We're only going to be considering stretching or shrinking about the x or y axis, or mere flipping about the x or y axis, and that's it. Now you might have said to yourself, well, okay, so if cosine is just a shifted version of sine, well, what's the specifics of the shift? Well, okay, I'll tell you. The cosine graph is just the sine graph shifted pi over 2 units to the left. Okay, so with that, you say, that's interesting. So does that mean that would mean this then? So if I take the sine graph and I want to shift it to the left, so if I'm going to shift it in the negative direction, I add next to the x variable, I'm shifting it horizontally, I'm going to add pi over 2. Okay, so based on what I just said, then I just shifted the sine curve to the left pi over 2 units. So that's what the sine curve is, or the cosine curve is. So is that correct? Yeah, that's exactly right. 100%. Put your calculator in radian mode, type sine of x plus pi over 2. It's going to give you cosine x. Okay, but you might say, well, okay, why can't we just shift it to the right? Pi over 2 units. What's wrong with, isn't that the same thing? Well, let's take a look. So if we shift this, the sine x to the right pi over 2 units, then what happens? Well, the issue is we get okay, if we shifted it to the left, you can see this comes here. And then boom, they're lined up on top of one another, the two curves. But if I shift it to the right, this comes here. It's close, but they're not lined up. So no, that's not the case. Sine of x minus pi over 2 is not cosine x. However, if you think about it, though, what it is if we shifted it to the right pi over 2 units, sine x, and then flipped it about the x-axis, then we would get cosine x. So to flip about the x-axis, what do? Well, you multiply you multiply the opposite variable that you want to flip about by -1. So, all of this is y is equal to sine of x plus pi over 2. We multiply y by -1, so that means we're doing this. Now wait, no, this is not correct, because I said that we need to do if we do this, so we shift it to the right pi over 2 units, and then multiply this by -1, now we've got cosine x. So if you type, what I'm saying is, if you type sine of x minus pi over 2 into your calculator, you're going to get minus cosine x. But if you typed in minus sine of x minus pi over 2 into your calculator, it's going to give you cosine x. So you see, we really want to stay away from any translations when we're thinking about a pure sine or cosine. But flipping or scaling about the x or y axis is fine. You still have a pure sine or cosine. We'll talk about doing this in a few minutes. Now, why are the sine and cosine functions so similar? Really not just similar, they're the exact same thing. One is just a shifted version of the other. Well, let's think about this. Okay, so the definition of trig functions. And we know that sine theta is y over r, and cosine theta is x over r. Okay, so we've tracked the behavior of sine and cosine going around the circle before when we analyzed the domain and range of these functions. So we know the domain is all real numbers. You can input absolutely any theta, and you'll get a value for sine and cosine. And then the range of both sine and cosine was going back and forth between -1 and +1. So why are these two functions so similar? Well, they're both the ratio of a side of this right triangle to the hypotenuse. And as you go around the circle, it's just the same pattern of the side of the triangle under consideration going back and forth between equaling the radius, either in the positive direction or in the negative direction, or equaling 0, right? So sine, when you starts with the y side has no length. Then as theta increases, the y side length increases to equal the radius, and then the y side length decreases back to 0, and then the y side length increases to that of the radius, but in the negative direction, then decreases back to 0. Okay, now what about the x side length? Well, okay, it's at 0, it starts out where the x side length is equal to the radius. Then as theta increases, the x side length decreases towards 0. Then you keep going, the x side length increases towards the radius, but in the negative direction. Then the x side length decreases back to 0. Then it increases again until it equals the radius. Okay, so you see, it's the exact same behavior as you go around the circle, but it's just that one of the functions is like shifted with respect to the other. At 0, the x side length is equal to the radius, and the y side length is 0. But then at theta is equal to pi over 2, the y side length is equal to the radius and the x side length is 0. But they're both doing the exact same thing going around the circle. Okay, so you can see that's why these, you can look at these two functions like they're identical twins. And that's the reason why both of these curves fall under a single name. They're just called sinusoids. If you hear that something has a sinusoidal distribution, that can be referring to a sine or a cosine, because in essence, it's the exact same curve. Okay, now, so the property that these functions are, they're repeating, right? They repeat over and over again. What kind of function is that? What does that mean? Well, if you remember this from algebra, this is a function. It's a type of symmetry of a function. Functions can have different types of symmetry. They could be an even function, an odd function, or they could be what's called a periodic function. Okay, so if a function is an even function, then that means if you plug in minus x into the function and simplify, you get the original function back. Okay, a function is an odd function if you plug in the minus x to the function, simplify, and you get minus the function back. Okay, now those are the first two potential types of function symmetry. Now there's only one more, periodic symmetry. So, we're just talking about functions here. Like, yeah, a circle could have more types of symmetry, but that's not a function. Okay, so what periodic symmetry was about was that if you take the function and you add some number to x, so you shift it horizontally by some amount, you get back the original function. Okay, so if we come to sine, it's not talking about, if you shift sine by pi over 2, you get cosine. No, what it's saying is if we shifted, if we did sine of x plus or minus 2 pi, you would get the same, the function would lie on top of itself, right? If we shifted it over this amount to the right, then you just get the function back, okay? And this p here is called the period. Okay, now here's the technical mathematical definition of a periodic function. And so the way it lays it out is that the period is always going to be a positive number. That's the way, that's the way you want to technically specify it. It's always a positive number. And the reason why is because the technical way of looking at it is, yeah, this is true. This is true. That's correct. However, to say this completely generally, you can take, like it shows here, you can take any integer multiple of the period. You could do this with any integer multiple and you're going to get the function back, right? And it could be a positive or negative integer. It could be 0 too, obviously, right? And so they just say that p is specifying as a positive number. It'd be confusing to make it negative because you could just make n negative if you want it to shift in the other direction, right? So let's just look at cosine, because cosine and sine are periodic in the exact same way. You could shift this 2 pi to the right or 2 pi to the left, or any integer multiple of 2 pi, and then the function will lie on top of itself, right? Now, something else, though, is that p needs to be the least possible positive value. So that's important to note, too. So I could say, if I look here, I could say so there's a start point. I can start anywhere, and then it starts again here. So from here to here, that's 4 pi. So I could say p is 4 pi, right? And that's not wrong, Because if I used p is equal to 4 pi in regards to the sine or cosine function, then this is going to be valid. However, you want to specify the p to be the smallest possible value, right? So I could also identify a pattern with 2 pi, shrinking that p down to 2 pi. Now, if I try to go below 2 pi, I can't. So like, yeah, okay, so start with a point here. If I shift it, it would be, what, pi over 2. I shift it. So this value comes back on the curve, right? That's the idea. When you shift it, if you leave the original curve, the original unshifted curve, you're trying to get every single point in unison to come back onto the original curve. Well, this point, I could go pi over 2. This point would come back onto the curve, but you can see not every single point is going to lie on top of the original curve. There's no way I can do that with a shift that's less than 2 pi for the sine or cosine functions. Okay, and so that's what the period means for a periodic function. And again, it should be clear to you that every single trig function is going to be a periodic function. Every single one, 100%. It should make clear sense to you why that's 100% going to be the case. And it should also be clear to you that based on the definition of what the period is, there is no way that any of the trig functions could have a period that's greater than 2 pi. That would make no sense. Now, maybe a trig function could have a period less than 2 pi. That we saw that wasn't the case with the sine or the cosine function, but maybe another trig function is going to repeat at an interval of less than 2 pi, but anything greater than 2 pi, there's no way. And we're actually going to see tangent and cotangent have periods of pi. And later we'll get into the specifics of why it works out that way, but you can think about it because, okay, tangent is y over x, so opposite over adjacent. It's positive up here, but then you have negative over negative, so it's positive down here, and then it's negative here. So these two are the same value of tangent, and these two quadrants are the same value of tangent. But then you might say, well, okay, but like sine, the first two quadrants are the same value, right? Opposite over hypotenuse. Y is positive here in the first two quadrants. So why doesn't sine and cosine and even the secant and cosecant have periods of pi over 2? Because it doesn't have that. Tangent also has the symmetry about the quadrants, right? The first and the third, the second and the fourth. Here you go from the first to the second, you're positive, and then the second to the fourth, you're negative. So you don't repeat the pattern until you get through a full rotation. Here you go with tangent, you go positive, negative, then you start again, positive, negative. Positive, negative, positive, negative, positive, negative, positive, negative. With sine, for example, or like cosine, whatever, it's like it goes positive, positive, negative, negative, positive, positive, negative, negative. Okay, so that's the first main property that we've identified about the sine and cosine function or their graphs. And again, the unshifted sine and cosine function are unflipped, or else we're not talking about the sine and cosine function anymore. So yes, we've graphed them. We can see what the shape looks like. But the first main property is that both the sine and cosine function they're periodic functions. They have periodic symmetry, with the period being equal to 2 pi for both. Okay, now here's where I want to give you the tip that I mentioned at the start of the video, which I think this tip is going to be really useful for you. Okay, so for the special case where you're dealing with a sine or cosine function and the horizontal axis is time, that's when additional terms will come in. So for example, you'll hear about the frequency of the sine or cosine curve. So what does the frequency mean? Well, okay, if this was a time axis, then the period 2 pi, that corresponds to a time, right? What it means is that it takes 2 pi seconds to go one full cycle of the sine curve or the cosine curve. The period is a time. Well, what the frequency is you just take you divide one, you do 1 divided by the period. And what that means is that it's always 1 every time, because it's 1 cycle. You're saying 1 cycle per how many seconds? If it was 2 pi seconds, then you're going 1 cycle every 2 pi seconds. Now, we're going to talk about later in the video how you can change the period by stretching or shrinking a sine or cosine curve about the x-axis. So it's not like the period has to be 2 pi, but no matter how much you stretch or shrink the curve about the x-axis, it's always just going to be, you take the frequency is 1 divided by the period. It's 1 cycle divided by the time it takes to go 1 cycle. Now, what I don't like about that, and here's the tip I want to give you, is that so there's a lot of cases where you're dealing with a sine or cosine curve and the horizontal axis isn't time. Like, let's just look at what we were doing from the start before this. The horizontal axis wasn't time, it was angle. And so typically the way it works is that you don't think about the idea of a frequency. Well, my suggestion would be you can let yourself think about the idea of a frequency even if the horizontal axis isn't time. Like, let's just say I'll throw out some random, what if the horizontal axis was hot dogs, number of hot dogs eaten. This is a hot dog eating contest or something, right? So, I don't know how that would follow a curve like this. So yeah, if this was hot dogs, then the period is 2 pi hot dogs. Now, again, you could adjust the period. We'll talk about it later. So maybe it's something that's, I don't know how you think about 2 pi in terms of hot dogs, but you get the idea. The period would be 2 pi hot dogs, and I'm not sure what the y-axis would represent, but then the frequency would be 1 in 1 cycle, you go through 2 pi hot dogs. You might be saying, well, how do you have not an integer number of hot dogs? Well, like a fraction of hot dogs, right? Maybe you've only eaten a certain amount of the hot dog. You can still think about frequency. It doesn't have to involve time for you to think about the idea of how much of a unit, so the unit on the independent variable, how much of that have you gone through in 1 cycle? Okay, so, just to clarify, the tip I'm giving you is when you think about a sine curve or a cosine curve, I mean, you could do this, I guess, with anything that's periodic, but just focusing on a sine or a cosine curve, the sinusoids, don't block out the idea of frequency just because you're not thinking about an independent variable being time. No matter what, every time you think about a sinusoid, you think about, okay, this has a period and this has a frequency. So we've learned about our second property of sinusoids. They're periodic with period p, and they have a frequency that's equal to 1 divided by p. And again, you're going to be different because you're not going to restrict yourself to think about the frequency only for the case where the period is time. You're going to always think about a sinusoid having a frequency, regardless of what the horizontal axis units are. And the frequency is always 1 divided by the period because it's 1 cycle per this amount of the horizontal axis units. Okay, and now another reason why thinking about it this way is so valuable, thinking about frequency this way is so valuable, is because now that you've opened the door to think about frequency for any sinusoidal curve, then you've now opened the door to think about the intimate connection of the sinusoids to a circle in all cases. So what do I mean by that? Well, okay, a sinusoid has a period, it has a frequency, but it also has an angular frequency. Okay, we know based on the definition of trig functions, and in particular, you don't have to have a circle to define trig functions, but there really is some nice symmetry and organization that comes into play whenever you apply the unit circle to the definition of trig functions. And, all trig functions you can relate to a circle because, you can relate to a circle because an angle goes, any angle, you can associate an angle going around a full rotation, right? It's like it's circular, right? But there's really a more of a close connection to the circle with sine and cosine functions because, as you know, with the unit circle, the coordinates of a point on the circle, on the unit circle, represent the sine and cosine of the associated angle, right? And this connection is most clearly illustrated when you make a setup like shown here, where, so here's the graph of sine. We know sine represents the y coordinate on the unit circle, and you can walk along the sine curve, and there will be this vertical alignment. As you walk along the sine curve, you'll be walking all the way to the across a period, going from 0 to 2 pi, let's say. Then you, at the same time, you'll be walking around the circle, and the heights will be lined up. If you put the center point of the unit circle along the x-axis here, the heights will always be lined up, right? This is y is equal to sine x. So this, like, symmetry, you can call it, this intimate relationship between the trig functions, but most closely with the sine and the cosine function, is really best illustrated with a diagram like this. Okay, now this is just an illustration. It's not like you might say, well, okay, we could do the same thing with cosine, just bring the circle down here. Well, no, it wouldn't work that way, because you'd have to flip, like the problem that what makes the sine work here is because the output axis of the xy coordinate system, the vertical axis is the vertical coordinate on the unit circle. If you plotted cosine, it's not like the output all of a sudden changes to the x coordinate. The output is still the y coordinate, right? So so you can't really do this with the cosine graph unless you flip the Cartesian coordinate system, unless you flip this 90 degrees to where the output is on the x-axis. So it only works out to where you can illustrate it like this with sine. But even without the illustration, it's still, cosine's the exact same intimate relationship, because cosine's just it's the x coordinate, right? As you're walking along the cosine curve, yeah, you can't like follow it visually like this, but still it's the x coordinate that corresponds to the point on the circle. Okay, and so now I mentioned angular frequency. What does that mean? Well, that's associated with the fact that with any sine or cosine curve, you could have a circle in the back of your mind. As you walk along any sine or cosine curve, you could be thinking about it at the same time, walking around a circle. And so if the idea is, if it takes, so let's just start with time. Let's just imagine the x-axis is time to start. If it takes, here it would be 2 pi seconds to go one cycle. Okay, so we have a period p, which is 2 pi in this case, a frequency 1 over p, one cycle per that much period, that much time. The angular frequency is, instead of, you're not going one cycle per that period, per that amount of time, you're going 2 pi, right? It's 2 pi divided by p. Now, the angular frequency is in radians per second, okay? But just note that radians are technically unitless. So these two have the exact same units. Frequency, yeah, it's cycles per second, but cycles is not, that's kind of confusing. Cycles is not, like hertz is, the unit of hertz is 1 over seconds. Frequency is in like 1 over seconds, that's hertz. The units are 1 over seconds. The units of frequency, or angular frequency, are 1 over seconds. Okay, so, it's important to understand angular frequency. We're going to see examples later in the book, but in physics and engineering, you'll see sine functions, cosine functions, that they have angular frequency within the argument. Like you'll use frequency, angular frequency, period, inside sinusoidal functions. Okay, but again, my tip for you, which I think is going to be really helpful, is it doesn't matter what units the period or the horizontal axis are in. If this was hot dogs, that's fine. Then it takes to go one rotation around that circle that is associated with the sinusoid. What's the angular frequency? How many hot dogs does it take to go a full rotation? 2 pi radians. That's the angular frequency associated with the hot dogs. Okay, so again, I just want to make this clear. It took to go one cycle. How many periods was like, not how many periods, it was one period, but a period might be 5 hot dogs. So to go one cycle, you have to eat 5 hot dogs. One cycle per 5 hot dogs, or 1/5 cycles per hot dog, right? Every hot dog you eat, you go 1/5 of a cycle. Or you can think about, okay, to go one period, which is 5 hot dogs, from an angular standpoint, for the associated circle, how many radians do I go around the circle every time I eat one hot dog? It's going to be 2 pi divided by 5. And so you get that as a decimal, and that means that you go that many radians per every hot dog you eat. Okay, so now we have 3 properties. Any sinusoid you come across, it doesn't matter what the horizontal unit is, who cares about time, that sinusoid, in your mind, you know it has a period, it has a frequency, and it has an angular frequency. And again, just to make this clear, because as you go along the sinusoid, at the same time, in the back of your mind, you're going around a circle, right? You can, as you walk along a sinusoid, you can, you're walking at the same time in the back of your mind around a circle. Once you get to the end of the period, you're almost at a full rotation of the circle. If you're at the middle of the period, you're halfway around the circle. Okay, now you might be wondering, you might not have said this to yourself, but maybe some of you might have thought about this. You might be thinking, well, okay, this idea of periodic, a function having periodic symmetry, I mean, that's not unique to sinusoids or trig functions. There's a lot of different periodic functions, right? That's true. Here's some examples. There's the sine wave, but okay, square wave, triangular wave, sawtooth wave. There's an infinite number of periodic functions that have nothing to do with trig functions, right? And you specify the period the same way, the smallest distance, or horizontal axis distance that this repeats. All of those were periodic functions based on this definition. Okay, and so then you might be thinking, okay, well, can't I do like the same thing with the analogy with the circle with any of those periodic functions? That is true. This triangular wave, this square wave, this sawtooth wave, if you had a horizontal axis in units of time or any other units, then, okay, it has a period, right? Well, then you take one cycle divided by the period, then that's its frequency. And then if I just think about, okay, so here's one period. Well, okay, if I'm a quarter of the way through the period, then I'm a quarter of the way around the circle. If I'm 3/4 of the way through, I'm 3/4 of the way around the circle. So I can think about an angular frequency from that perspective. Yeah, you can do that. However, the sinusoids are extra special in this regard because there's no other periodic function that you could do something like this with. And then you could do this with cosine if you just flipped if you rotated the Cartesian plane 90 degrees, you could do this with cosine. For example, let's take this sawtooth wave. Let's put a period here, I guess something like that. Okay, so once you're halfway through, well, this point is over here, which is not a big deal. I mean, you could still, I'm not saying you can't say this, look at this as having an angular frequency, as anything periodic with an angular frequency. I'm just saying that the sinusoids have the most intimate connection to the circle. Okay, now you might say, well, wait a minute. No, let's bring in the square wave. We can make this work. So we'll do this. Yeah, there we go. Well, no, they're not going to line up. When you start here, the point in the circle's down here. In fact, other than with a sinusoid, I don't think there's any way to get them to line up 100% of the time all the way through the period. Okay, now you might be thinking, well, okay, yeah, that's pretty cool, but we can only do this with a unit circle, though. Well, no, that's not true at all. That's why when you think about anything circular motion, whatever, Ferris wheel, anything, you could think about sine functions, in particular the sinusoids, no matter what the size of the circle. And if that confuses you, then what's tripping you up is that, so yes, we can, if we change the radius of the circle to something bigger, so we're going to scale, in a second, we'll scale sine and cosine up about the y-axis or down. Yeah, so if you have a circle that's not radius of 1, then you've lost the definition of trig functions, where you just like read off the coordinates and that's like the definition of sine and cosine. That's true, but you haven't lost any ability to be walking along the curve and you're following, you're tracking at the same time around that circle of radius other than 1. So here's what I mean. Let's take a look at that. Okay, so we're studying the properties of sine and cosine. We're just starting with the basic y is equal to sine of x and y is equal to cosine x. Okay, now we're going to go ahead and start thinking about applying transformations to these graphs. We learned about transformations in detail in algebra, but we're going to talk about now stretching and or shrinking about the y or x axis, as well as flipping about the x or y axis. Okay, and so what we learned is in algebra, if we want to stretch or shrink about the y-axis, what do? And the idea of stretching or shrinking about the y-axis is this. So let me... Okay, what it means to stretch or shrink about the y or x axis is if I wanted to, so just the basic y is equal to sine x that we've just looked at. If I want to stretch this graph about the y-axis by a factor of any number, so if I want to shrink it, it would be a number that's less than, it's going to be just a positive number, or no negatives because we're not flipping. So any positive number, if I wanted to shrink it, it'd be a number less than 1, stretch it a number greater than 1. What that means is that what I'm wanting to do is this has, every point on this graph has coordinates x and y on this graph. If I want to stretch it or shrink it about a factor of a, I'm wanting to not touch the x values and multiply the y, every single y value by that factor. And if I wanted to stretch or shrink about the x-axis, it's the same idea. I don't touch the y values of every point, but I multiply every single x value by that factor. Okay, so how do I, if I wanted to stretch this about the y-axis, so let's say I wanted to multiply every single y coordinate by 3. Then what I do is I come to every single y variable in the equation, which for a function, there's just going to be 1. And I come right in front of it and I multiply it by the reciprocal of what I wanted to stretch it by, the reciprocal. So I want to multiply every single y coordinate by 3. I want it to get bigger in the y. I multiply this by the reciprocal, the y value. And so if you multiply both sides by 3, this is the result. Okay? Now, let's use cosine x as an example. Let's say I wanted to shrink. I want to multiply every single, it starts with xy. I want to multiply every single x coordinate by 1/5. I want to shrink it about the x-axis. So I come to every single x variable in the entire equation. In this case, it's just 1 here. I come right in front of the x variable and I multiply by the reciprocal of the amount that I want of this. So, okay. So, here's sine x. If I stretched or shrunk about the y-axis, and that's all I did, what's going to be affected is what's called the amplitude of this sinusoid. The amplitude. The amplitude is, you take this distance here, the distance, the entire range, which goes from -1 to 1, and you divide it by 2. So it's the amplitude is this height here. That's the amplitude. Okay, and that's how you think about a stretching or shrinking about the y-axis of a sinusoid. What you're doing is, if I did y is equal to 2 sine x, then I'm multiplying the amplitude by 2. That's the way you think about a stretch or a shrink of a sinusoid about the y-axis. Okay, and so that's another property of the sine and cosine graphs. They have a period, a frequency, an angular frequency, and an amplitude. Okay, so shown here is sine x, and this is 2 sine x. You see, the amplitude is the main change here. And it makes sense to think about a scale, a stretching or shrinking about the y-axis of a sinusoid this way, because that's in essence all that's happened, is that the amplitude has increased or decreased. Here it's increased. And what I mean by that is you can see that the nature of the sinusoid, the general shape is exactly the same, other than the only difference being the amplitude has changed. Okay, so here, if this became y is equal to 2 sine x, then this amplitude would be scaled up. And you can think about, at the same time, just changing the radius of this circle to 2. And as you walked along this y is equal to 2 times sine x, it would be the exact same symmetry between the sinusoid and the circle. Nothing would change. But the change would be that you might think in your head, well, okay, so why can't we define trig functions with something that's not a unit circle? That there would be a change from the standpoint of the coordinates of the circle, of the radius 2 circle. The coordinates would be based on 2 times sine x, which is not a definition of trig functions, right? There's no factor of 2 in the definition of trig functions. So when we make the radius 2 and multiply this by 2, we've deviated away from the meaning of trig functions, the definition of trig functions. That's it. But we have not deviated away from the fact that there is an angular frequency of the sine graph. There's this intimate connection of the sine graph and the circle. Okay, now what about stretching or shrinking about the x-axis? Right, if we did cosine of 5x here, let's use the cosine graph as an example. Okay, so again, the properties of a sine or a cosine graph, we know it's period, frequency, angular frequency, and amplitude. And the stretching about the y-axis, you can really think about it as it's a change in amplitude, because we saw the basic shape was the same. It didn't change at all. It's really just the amplitude that changed. That's the way you can think about it. Okay, well, when it comes to a stretching or shrinking about the x-axis of sine or cosine, what's changing, what you can think about as fundamentally changing, the way we thought about amplitude, is the period, which is, that's associated with the frequency, because frequency is 1 divided by period and angular frequency, but we can just think about it as the period. That's what's going to change, is the period. A stretch about the y-axis of a sinusoid, we're just thinking about sine or cosine, untranslated vertically or horizontally. A stretch or shrink about the y-axis, you can think about that. It's great to sum that up as a change in the amplitude of the sine or cosine. A stretch or shrink about the x-axis, you can think about fundamentally as a change in the period. And in the same way, if you stretch about the y-axis by 2, that also multiplied the amplitude by 2. If we shrink about the x-axis by 5, it's going to divide the period, it'd divide the period by 5. Okay, so let's do cosine 5x. That's a shrink about the x-axis by a factor of 5. Okay, so there's cosine 5x, and the blue is cosine x. So you can see the period was about 2 pi, 6 point something. So let's see, 2 pi divided by 5, 1.25-ish. So there's 2, that would be 1, this would be about 1.5. Yeah, there you go, about 1.25. That's we start here, we're back at 1 cycle. And then notice the amplitude didn't change. Okay, and then also notice it's really useful to think about. You can summarize these transformations as just a change in the amplitude or the period, because the fundamental shape didn't change. The fundamental shape is exactly the same. Okay, now let's talk about flipping. So once again, as we learned in algebra and transformations of graphs, we could take a function like sine x or cosine x and flip it about the x and or y axis. So for example, let's flip sine x about the y axis. What this means is that we want to take the graph y is equal to sine x. It has points x, y on the graph. And what we're wanting to do is we're wanting to flip about the y-axis. We want to multiply every x coordinate by -1 and not change the y coordinates. And we want to do this because if we have a point, for example, here, x, y, then we want to multiply the x coordinate by -1 and not change the y coordinates, so we've flipped about the y-axis. Okay, and so to do this, we go to every x variable in the entire equation. There's only one in this case, and we put a -1 in front of it. Now, the sine function is an odd function, so we get, so the graph minus sine of x is sine of x flipped about the y-axis. Okay, now if we want to flip about the x-axis, let's just use cosine x as an example. So what we're wanting to do is take the cosine graph with points x, y. We're wanting to leave x coordinates unchanged and multiply all the y coordinates by -1. So what we do is we go to every single y variable in the equation. There's only one in this case. And we put a -1 in front of it. So y is equal to minus cosine x is y is equal to cosine x flipped about the x-axis. Now, if we try and flip cosine x about the y-axis, nothing happens because it's an even function. Cosine x is symmetric about the y-axis. If we flip sine of x about the x-axis, we get the exact same result as if we flipped it about the y-axis. So again, the red curve is sine x, blue curve cosine x. You can see how with cosine x, there's no flipping about the y-axis. If you do that, you just get the cosine curve again. That's why y of minus x is just equal to y of x. But you see, we can flip cosine x about the x-axis. This point will come up here, for example. This point will come down here, for example. And same idea with sine x. We can flip sine x about the x-axis. So the dotted lines represent each curve flipped about the x-axis, and there you go. Flipping either sine or cosine about the x-axis is just like multiplying the entire function by -1, which makes sense. Y is equal to minus cosine x is cosine, the original curve cosine x, flipped about the x-axis because you're just taking each function value, the output value, which is the y-axis, and just multiplying it by -1, so it's going to the other end. And same idea with sine x. Now with sine x, if you flip it about the x-axis, flip it about the y-axis, you can see how you just get the same result, y is equal to minus sine x. Let's come back to sine x. If we flipped it about the y-axis, you get the same result. And the reason for this is because odd functions, which sine x is, are symmetric with respect to the origin, which means when you flip them about the x-axis and then flip them about the y-axis, you get the original function back. Okay, so now you understand the properties of the sine and cosine function, and you understand what happens to these functions if you stretch or shrink them about the x or y axis or flip them about the x or y axis. As long as you don't perform any translations, then you still have a pure sine or cosine function, because what you may have noticed is that even if you stretch or shrink about the x or y axis or perform any kind of flip, the cosine curve is still an even function and the sine curve is still an odd function, and they both still retain their characteristic features. For example, cosine remains as having its highest peak or highest trough at the origin, and sine remains as having an x-intercept at the origin. But once you start to translate, then you either switch from sine to cosine or switch from cosine to sine, or you've got a sinusoid that's like a mixture of both sine and cosine. So if we start to shift cosine to the right, once we got past the halfway point to getting to the sine curve, then we've really got more of a sine curve than we do a cosine curve. You could say it has more of a sine. Once you get past the pi over 4 point, because we need to shift pi over 2 to get to the sine curve, once you get past pi over 4 shifting, you really have more of a sine curve than you do a cosine curve. Okay, what else? Well, okay, if we think about the domain and range of the sine and cosine function, the domain is all real numbers. That makes sense. And we know that that sine and cosine only go from 1 to -1. So you can't get any value if just putting into basic sine and cosine. There's no way to get a value that's greater than 1 or less than -1, and that's what we see. Okay, we notice that if we look at a period of sine or cosine, let's take a look at sine, 0 to 2 pi, there's going to be two x-intercepts. So, you pick one, you'd have to just pick one endpoint to be included in the period, right? So if you say that that 2 pi is included in this period and not 0, or maybe we could say 0, I mean, whatever, but there's going to be two x-intercepts, and there's going to be these two peak points. For every single period, there's two x-intercepts and there's two peak points. Okay, and what's great about these points here, these unique features, is that no matter what, they're always equally spaced across the period. So this first peak is going to be 1/4 of the way across the period. This first x-intercept will be halfway across the period, and this trough here will be 3/4 of the way across the period. And then the second x-intercept will be at the end of the period. And yeah, I forgot to mention, when it comes to the symmetry, even in odd symmetry, and even with what I just talked about with the peaks being evenly spaced, these features, these properties are satisfied even if you apply one of the transformations, the scaling about the x or y. If you scale about the x and change the amplitude, you're going to have the cosine is going to be even, sine is going to be odd, and each period is going to have these features, the peak and the peak and the trough, and the two x-intercepts across a period equally spaced. No matter how you scale the x and y axis, no matter what combination you do to scale the x and the y axis, those features are satisfied. Okay, and so to put numbers to these features, we'll have an x-intercept with the sine graph at n pi, where n is any integer. Right? This is pi, 2 pi, minus pi, or minus pi, minus 2 pi. So n pi, you'll have an x-intercept for sine x. Again, the graph is not shifted. And then you'll have a peak or a valley at, let's see, that would be at an odd integer multiple of pi. Right? So n is equal to 0 at pi, n is equal to 1 at 3 pi, or no. So it would be an odd integer. There's an odd integer involved divided by 4. So at 0, n is equal to 0, you've got pi over 4. There's pi over 4. Or no, this would be divided by 2. This is, okay. N is equal to 0. This is pi over 2. This is pi, 3 pi over 4. Yeah, n is equal to 0. You're at pi over 2. N is equal to 1. You're at 3 pi over 2. This is 3 pi over 2. And same idea in the negative direction. Then n is equal to 2. You're at what? 5 pi over 2. So yeah, this should be, yeah, this is the peaks and the troughs for the sine graph. Now for the cosine graph, the x-intercepts are going to be at 2n plus 1 over 2 pi. And then the peaks and the valleys are going to be at n pi. Okay, and now just to further illustrate how the sine and the cosine graphs are identical twins and how it makes sense to refer to both curves as the same name, just sinusoids. Later in school, you'll learn about, and we might, I think we might cover this in this course as well, but you can take the sum of a pure sine function and a pure cosine function and get just a sine or a cosine function that has been shifted left or right by some amount, which technically once you shift a sine or cosine function, then it's not a sine or cosine function anymore, right? It's some mixture of the two. But I'm going to write an equation up here. There's a bunch of variables in it. Don't worry about all the variables. I'm just trying to give you a sense of the close connection between the sine and the cosine. So you could take, so alpha 1 sine of bx. This is just some coefficient. This is just another coefficient. But this is a pure sine function, right? It's still a pure sine function if all you've done is scale it about the y and the x. As long as you haven't shifted it or flipped it, it's a pure sine or cosine function. Okay, plus alpha 2 cosine of bx. Okay, you're adding to this a pure cosine function, and what you get is so this isn't, once it's shifted left or right, it's not a pure sine function, but it's just an expression of sine. You took a pure sine function and a pure cosine function, and you can get just an expression of sine. And you could do the exact same idea with cosine if you wanted to, by just like adding pi over 2 inside here, for example. Okay, so that gives you a sense of why the sine and the cosine functions are really one and the same, and that's why their curves are collectively just referred to as, in general, as sinusoids. Okay, so there you go. Long video, but that gives you the full overview of the sinusoids. Now we're going to work a bunch of examples, and then in the next section, we'll open the door to translating these vertically or horizontally.